Yes, I can see it.
Okay, all right. And is my audio clear?
Your audio is clear.
Okay, all right. So let's start then. Okay, so this is the second part of the lecture of basics of synthetic aperture radar. We had the first course before, and this is the second part. And in the last lecture, we discussed about the basic theory of SAR and its image formation. We also talked about the radar parameters. And today we are going to talk about how SAR interacts with the surface, and we will also focus on ground parameters and those parameters that influence backscatter. Right. Okay, so radar backscatter, we have discussed that before in the previous lecture. It's very important in SAR images, and there are two surface parameters that influence backscatter. Those are dielectric constant and surface roughness. So the brightness of the feature in SAR image is dependent on the portion of the reflected energy that is returned back to the radar sensor. However, the magnitude or the intensity of backscatter depends on how the energy or the signals interact with the surface. So this energy is a function of different variables, such as radar parameters, surface dielectric, and the structure of the surface. So surface roughness is a key factor in observing the changes on the radar image. Normally, surface roughness is the average height variation of any surface as compared to a plane surface. And it depends on the wavelength and incident angle, whether the surface appears smooth or rough to the radar. So the surface will be considered smooth if the surface variation will be smaller. And the surface will be considered rough if the variations are higher than wavelength. So it means a surface will appear rough as the wavelength gets shorter, and it will get smoother as the wavelength gets higher. And a rough surface will appear light in the tone of brightness, while a smooth surface will appear dark in the SAR image. Let's not forget the dielectric constant, which is also the indicator of conductivity and determines the intensity of a reflected signal. Right. Okay, let's start with the dielectric constant. Well, a dielectric constant is a fairly complex phenomena, but in simple words, dielectric constant is the measure of electric properties of a surface material, of any surface material. Actually, the presence and absence of moisture drives the dielectric. It means if there is moisture in the surface, there will be a dielectric effect. So the dielectric property of a material influences its ability to absorb microwave signals or energy. So in short, we can say that the dielectric is an indicator of conductivity and reflectivity. And the strength of a backscatter signal that goes back to the sensor is proportional to the dielectric constant of the surface. So for example, for dry materials, the dielectric value ranges from 2 to 8, and for the watery surface, it ranges between 40 to 80. So therefore, the moisture in the soil or vegetation can influence reflectivity. That is why sometimes normally the reflectivity or image brightness increases with increase in moisture, which also means there is less penetration through the medium. So sometimes, therefore, soil and vegetation will appear bright when they are wet, and they have a dielectric constant effect, and they appear bright because of the reflection, and they might appear dark when they are dry. The lower the dielectric is, the more energy is absorbed and darker the image will appear. Right, So now the radar interaction in the with surface reflection. Okay, so the surface smoothness or its roughness is in respect to radar depends on wavelength and incident angle of the microwave energy or the signal. A smooth surface is, or we can also call it a specular reflector surface, will tend to reflect the microwave energy in one direction, as we can see in the B part here. It will go away from the sensor. That's why smooth surface tends to appear very dark in the radar image or SAR image, because all the backscatter energy is directed away from the sensor. On the other hand, a rough surface will scatter radiation in all directions. Objects like building, they have the right angle. So with the right angle or the corner reflector cause microwave energy or the signal bounce off both surface and the sides of the feature and direct the majority of the signal back to the sensor. That is why we can see the buildings are bright in the radar image. All right, so as I said, flat surfaces generally appear black or dark because of the energy is being reflected away from the sensor. And also a calm water body will also appear dark in the radar image, but sometimes it can appear a bit grayish because of the surface of movement of waves, sorry. And a forest canopy is an example of rough or diffuse surface and will appear also gray in the color with varying texture. So rougher surfaces, they scatter more energy, but in all directions, including back to the sensor. So some of the energy goes away from the sensor, some of the energy goes back to the sensor. Therefore, rough surfaces appear mostly bright. And surface roughness is also described as a function of wavelength and the angle of the incident coming from the radar sensor. Depending on the wavelength and the angle of incidence, the surface may produce different backscatters. So it depends on the angle and wavelength. Right. So generally, if a plant canopy is dense, there will be a strong backscatter. For example, vegetation that has greater or like higher moisture content will return more energy. That drives vegetation than drier vegetation. So the moisture in this canopy that will be the reason of more reflective energy. So the wavelength of the microwave signal or energy can change the relative amount of backscatter depending on the vegetation type. Radar can also be used to identify different types of vegetation by comparing the amount of backscatter from different receiving bands of our wavelengths. In this picture, we can see there are some areas in these kind of forest. Both radar image, in this picture, in this one, sorry, yes, this one. Okay, so in this picture we can see two pictures. Both are of the same area but different wavelengths or different bands. The left one is the C band and the right one is L band, and both looks almost similar to each other, but there are more darker areas in the right one. The reason is because L band has a bigger wavelength, so it can penetrate more deeper into this forest, and that is why we can see more darker areas. And the bigger darker areas are parts of lakes, and that's water. That's why we can see it as black or dark. Right, so there is another way we can identify many other things, like using radar sensor. We can also identify the oil split in the sea, and here is an example. Let me tell you why we can identify this. Is because when oil split on the water surface, it's smoothen the surface, so it stays still on the water surface. That is why the reflective energy goes away, and we can see it as black, because it's a very calm, smooth surface. So this is the example that we acquired, not I acquired, I took an example. It is in the area, Yellow Sea area, on December 11, 2007. A oil tanker was, was crushed, and all the oil was split onto the surface of ocean, and we can clearly identify those areas where this oil has spread over the surface of ocean. Also, we can use SAR images for land cover classifications. Also, there are composite images in SAR data, which we can use to classify our images, and it's not okay. So it can be used for both land use and land cover classification, yes, as I said. And on the right side, we can see a composite image of SAR. So in the classification results, however, may vary. Actually, it depends on the polarization. So what kind of polarization you have. Is it a VV, VH, or V or H? So it depends on the polarization. So based on the polarization, the results of classification may vary a little bit, or maybe more than that. Right. Okay. So there are several radiometric and geometric distortions that we normally have to correct before using the SAR image. Now we will discuss those distortions. The first one is slant range distortion, and slant range scale distortion occurs because radar is measuring the distance to feature in slant range rather than the true horizontal along the ground. So this results in varying image scale, like moving from near to far range. Like as we can see in this picture here on the right, this target A1 and B1 are of same size, so on the ground, but their apparent dimension in slant range are different. So as we can see, their size has been changed. So this caused the targets in the near range to appear compressed relative to the far range. But using trigonometry, ground range distance can be calculated from slant range and platform altitude, and then we can convert it to a proper ground range format. So this conversion comparison shows a radar image here. Okay, in the left side, we can see a comparison image, where on the top we can see a compression on the left side, where a road and the field is compressed. But when we corrected the image, now the length has been changed, and the viewing angle has been also changed. So the feature looks proper now in the second image, which is down below here. This one is not corrected, and this one is corrected according to the geometric shape, which has the proper geometric shape. Okay, so similar to the distortions, we have this one, foreshortening and layover. Like for example, in simple cameras and scanners, we also have some kind of distortions, and also radar image are also subject to geometric distortions due to the relief displacement. So radar, foreshortening, and layover are two main consequences in SAR images. So when we look at the picture, in normal case, the top, like in this one, foreshortening part here, this picture, in the normal case, the top of the mountain should be geographically located beneath it onto some reference surface. But because we measure the signal coming back as a function of range, therefore the projection sometimes, not sometimes, most of the time, is not in correct position. So when radar beam reach the base of a big feature or tall feature tilted towards the radar, in this case, which is mountain, before it reached to the top, so the foreshortening occurs. Again, let's see, because the radar measured distance in slant range, so the slope of AB will appear compressed in real in the SAR image. So as we can see, the distance between A and B, this is the length of A and B, and what we will see in radar image will be A dash and B dash, so it will be compressed. So yeah, this will happen. And also on the other side, when the maximum foreshortening occurs, when the radar beam is kind of perpendicular to the slope, such as here in the case of C and D. So in this case, you know, the base and the top of top image simultaneously are exposed to this kind of foreshortening, which we call maximum foreshortening. It's when radar is perpendicular, as I said. So in this case, the length of the slope will be reduced to, we can say, an effective length of 0. See here, the length of C and D is this one, but what we see in the SAR image will be C dash and D dash, which will be almost 0. So in the second case, layover occurs when radar signal or radar beam reaches to the top of any feature, or for example, mountain or building, top of the feature before it reaches to the base. So in this case, the signal will reach to the point B before it reaches to the point A. So it will return back. The B signal will also return back, and the the signal A will return later. So in this case, we will see B first and A later, and as we can see here. So in this case, the instead of shifting towards the radar, it will look like that it's totally flipped. So normally, in simple words, we can say that in foreshortening, like the tall buildings and tall mountains, they look like they are kind of leaning towards the sensor. So if the sensor is on the left side, as we can see here, the features of mountains, they are leaning towards the sensor, and in the layover, it looks like they're totally flipped over. Yeah, these are the two cases of this one. Okay, so all right. Oops, this is not okay. Sorry. All right. Okay, this one, yes. In this example, you can see that before correction and after correction, these are foreshortening that are corrected. Here in the left image, we can see that all the mountains are leaning left side, and after the correction, we can see their original and real shape. Right. So both foreshortening and layover, they result in shadows. So radar shadow occurs when beam is not able to illuminate the other part of the surface, and shadows occur in the downrange behind the vertical features or slopes with steep sides. So since radar beams cannot illuminate the other surface, the shadow region will appear very dark or black because there is no energy in the background, and not background, in the sides where there is no backscatter. So as the incident angle increase from near to far range, the shadow effects also, you know, be vary and look more oblique at the surface. And this image shows how the hillsides are showing the shadows in case of radar gets in contact with the high mountains. Right, and because it's all because the radar is side-looking. So due to the side-looking observation, the geometry of SAR images are subjected to these radiometric distortions and also geometric ones that we have just discussed before. So in addition to geometric mislocation of pixels in some areas, the oblique image of illuminating radar energy adds also topographic shading to the true surface. It also that gives sensor facing side of hill slope a overexposed appearance. Like in this one, we can in the left image we see the overexposed ones in the hills, and here we after the correction, these overexposed surfaces are dimmed down a little bit. So both these effects of radiometric and geometric distortions, they hamper the use of SAR image in many applications. So sometimes, not sometimes, maybe most of the times, radiometric modulations often disguise the radar reflectance or absorption and reduce the applicability of radar studying many properties of surface. So also these kind of distortions may add problems in change detection and because they overexpose some areas, so it might make it difficult. So in short, before using this radar image, it is advisable to correct these distortions. All right, so that was it for this. Oh, I think I missed one other distortion, which is speckle. I forgot to add it here. So normally speckle is the salt and pepper effect that we can see in the SAR images, and it can also be removed by there are two methods. One is the multi-looking, and the other one is I forgot the name of that one, but there are two methods that can remove the speckle noise also. All right, so that was it for today's lecture, and in the next one we will start to introduce the processing of SAR data and its analysis. Thank you so much. If there are any questions, please, you can ask.